Hello everyone, my name is Aditya Bansal from the School of Computer Science and Engineering, and today I'm going to present my final year project on the topic of neural network compression techniques for out-of-distribution detection. To give a brief overview, one of the key challenges in deploying machine learning models on embedded systems are the numerous resource constraints, for instance, memory footprint, response time, and power consumption. Such real-time systems require resource-efficient models with low inference time while maintaining reasonable accuracy. In the context of out-of-distribution detection, despite the detection model having a high classification accuracy, if the inference time is too high, the system might be rendered ineffectual. In this study, we implemented a number of compression techniques on real-time embedded system of the Duckiebot by studying the performance of these methods, particularly for the task of OOD detection. The compression techniques of pruning, quantization, and knowledge distillation have been experimented with and analyzed on numerous metrics. For example, execution time, memory usage, reconstruction loss, and OOD metrics like ROC curve, true positive, and false positive rates. Now let's look at various neural network compression techniques. Network compression by pruning the network weights is one of the most popular techniques, which is commonly used to reduce the number of parameters in a pre-trained network. The concept dates back to 1990, which was discussed by Jan LeCun in the paper Optimal Brain Damage. The fundamental idea is to remove the redundant and inconsequential parameters from a neural network. Such pruning could involve either removing individual parameters or removing groups of parameters, such as entire filters or channels from a convolution layer. Hence, the pivotal task in network pruning is to evaluate the importance of neurons or weights in a model and remove the ones that contribute the least to the output or inference of the model until the desired compression is achieved. The figure on the slide shows a simple illustration of the state of a network after pruning. Moving on to quantization, the compression technique of quantization has proved to be successful in both training as well as neural network inferences in research and industrial settings. Fundamentally, quantization consists of techniques for reducing the precision of weights and activations in a neural network. By storing tensors at a lower bit width than the floating point precision, drastic improvements can be made into the model computations as well as storage of such models. A quantized model executes some or all of the operations on tensors with integers rather than floating point values. Such compressed models can utilize high-performance vectorized operations on specialized hardware platforms while retaining high inference accuracies. The figure on the slide shows how the weights of a network can be converted from floating point 32 to int 8 values. Finally, moving on to knowledge distillation. Knowledge distillation aims to compress neural networks by distilling the knowledge from a larger complex model or an ensemble of models to a simpler and smaller model with minimal loss in accuracy. The technique was first successfully implemented for supervised learning models. Knowledge distillation is typically performed on complex neural network architectures, which might potentially be overparameterized. Hence, by distilling the knowledge to simpler models, more efficient architectures could be trained for deployment on resource-constrained devices. As illustrated on the figure in the slide, knowledge is distilled from a larger teacher model to a smaller student model by minimizing the distillation loss while training the student model. Now let's have a look at the methodology used in the experiment. The data was collected using a Duckiebot, which is a small autonomous vehicle consisting of a main onboard sensor, a front-facing camera, and actuators, including 2 DC motors, for moving in different drive configurations. Being fully autonomous, all the processing and computation was done on board on the Duckiebot using Raspberry Pi and NVIDIA Jetson Nano boards. In addition, the data was collected in the Hardware and Embedded Systems Lab at NTU, and the different tracks are illustrated in the slide. In the experiment, varying brightness levels on the track were considered. The dim and normal lighting conditions were considered as in-distribution data, whereas the high brightness track was out of distribution. Now let's have a look at the neural network architecture used for the autoencoder. The entire architecture consists of 2 parts, the encoder and decoder, which are shown in green and red respectively. The encoder consists of 4 convolution blocks, shown in yellow, consisting of 2 convolution layers, followed by 2D batch normalization, leaky ReLU activation function, and finally a max pool 2D layer. The convolution blocks were followed by 4 fully connected layers, shown in blue, and a leaky ReLU activation function. Similarly, the decoder is typically an inverse of the encoder part, which tries to reconstruct the original image from the encoded form. The decoder consists of 4 fully connected linear layers and leaky ReLU layers with an increasing number of neurons in each subsequent layer. The fully connected layers are followed by 4 deconvolution blocks, each consisting of max unpooling, conv transpose, batch normalization, and leaky ReLU activation functions. Now I'll briefly describe the entire OOD pipeline used in the experiment. First, the beta VEE model was trained on the in-distribution data gathered in different lighting conditions. By minimizing the total loss, that is, the reconstruction loss and KL divergence multiplied by beta, the model was trained for 200 epochs. Post-training, the weights file on the complete model is stored. Thereafter, since the beta VAE OOD detection technique operates on the latent variables generated from the encoder part of the model, the weights of the decoder part are discarded and the encoder-only model is used for the OOD detection. After that, by using a calibration set drawn from the same distribution as the in-distribution data, the calibration of the model is performed, where for each data partition, such as rain or brightness, the encoded latent variables are ranked based on their amount of variance for the corresponding partition. This step generates a JSON file containing the ranking information of the different latent variables. Thereafter, the OOD detector is run on the test set using the encoder-only beta VAE model and the calibration file on the test dataset. This step generates CSV files containing the execution time of each major step in the detection process, as well as the OOD outputs and ground truths for each test run. After that, the resulting files from the OOD detection are then used to calibrate the decay term of the OOD detector based on the ROC curves and the area under them. Finally, the evaluation metrics for accuracy, execution time, memory footprint, and OOD performance are recorded. Moving on to the results and discussion. The plots on the right illustrate the total reconstruction loss versus the number of epochs for the train and validation sets. It can be observed that the model training converged after about 80 epochs and the training was early stopped due to no further decrease in validation loss. The table summarizes the minimum loss achieved by the model on different data sets, where the total reconstruction loss is the cross-entropy loss plus the KL divergence into the beta value. It can be observed that the model was able to reconstruct the images from original inputs with reasonable performance. It can be seen that the dimly lit images tend to have higher noise in the reconstructed images. The trained beta VAE model was then further analyzed in terms of the execution time across different layers and how the values of the weights in the network are distributed. The total execution time for a forward pass was approximately 150 milliseconds. The plot on the right shows the layer-wise distribution of the execution time for inference. As expected, the convolution layers take up most of the execution time during an inference. Particularly, the second convolution layer of the decoder was the most expensive operation, followed by that of the encoder. This slide shows the results obtained after pruning the network. It can be observed that the total loss does not deteriorate until even about 80% of the nodes are pruned. In addition, a similar observation can be made from the reconstructed images. From the plot on the top left, the top 6 layers pruned were also plotted. It shows that the dense layer 1s in both the encoder and decoder were the layers which were pruned the most. 3 different quantization techniques were tested, namely dynamic quantization, post-training static quantization, and quantization-aware training. These techniques were analyzed across various time, memory, and performance metrics, and the different OOD metrics, along with various neural network hyperparameters. The below table summarizes the results obtained from the different quantization techniques and plots as compared to the baseline accuracy. It can be observed, dynamic quantization results in the least total loss since the quantization takes place during runtime, that is on the fly, and hence it can effectively compute the quantization scaling factor for each instance. Further, quantization-aware training results in the highest OOD metrics in terms of true positive rate, false positive rate, and the AUROC values. In knowledge distillation, the original beta VAE model was used as the teacher model to transfer knowledge to smaller compressed models. 2 different student architectures were used. The table summarizes the number of parameters, model size, and the total model loss for different architectures. Further, it can be observed that the student architecture 1 leads to a relatively better area under the ROC curve performance, but there's a loss in the true positive rate, whereas the student architecture 2 has very poor performance in all metrics. This implies that the convolution layer contains important information necessary for OOD detection, and hence the layer cannot be removed from the architecture. Finally, following are some demonstration videos of the Duckiebot taken during data collection. Thank you.